So once something fails, then it's always it's always the NDT person. But up to that point, nobody really knows what we do. We're kind of like the ghost that sits in the background to make sure that nothing fails. And so until something goes catastrophic, nobody knows who we are or what we do. And so it kind of creates a mystery behind it.
Welcome to another episode of Inside IALR. Thanks for being here today. So today we're here to talk about non-destructive testing, which, as I say when I give tours, is exactly what it sounds like, and we'll get into more of the specifics of what that means. But essentially, non-destructive testing, you are testing something without destroying it. So they named that field very well. So I have two guests with me today, and I'll let them introduce themselves real quick.
Yeah, I'm Caleb Ayers. I'm one of the NDT instructors.
My name is Michael Donnelly. I'm the NDT manager at the Center for Manufacturing Advancement, working for Industrial Inspection and Analysis.
So I gave my layman's understanding of non-destructive testing up front. I want you guys to give me your 20-second pitch to someone who has no clue what NDT is that you give, and then break it down further for when you're talking to smart people that know what you're talking about.
So my spiel for students who don't actually know anything about it, and it's the first time they're coming to the understanding of what it means, is a way to evaluate materials in such a manner that you can just inspect anything, right? So roller coasters, bridges, roads, vehicles, you name it, if there's a life attached to it, we're inspecting it, right? So helicopters, airplanes, anything that you actually get onto and transports a person or has some kind of life attached to it, we evaluate to make sure that whoever's actually using that product will end up surviving.
We test stuff without breaking it. It's in essence is that simple, and but it's very complicated once you start digging in. We test stuff with different modalities, different forms of energy to test different parts and depths of parts and welds. It's one of the super cool industries where I think you can do anything you want to do, almost anywhere you want to do it.
So just for those listening who don't know, Phil and Michael are involved in two different programs here at IALR, and I'll give kind of a brief explanation of what those are. So the ATDM program, Phil is an instructor for that, teaching students who will go on to work in defense manufacturing careers. So that program is accelerated training in defense manufacturing. So Phil is one of several instructors we have just for NDT, where they're training students for NDT careers, students who have no previous experience in this mostly. In 4 months, they can learn the skills for an entry-level NDT role to then be able to move up in that field. Michael is with the Additive Manufacturing Center of Excellence, or the AMCOE. We love acronyms here, which is essentially they're making the recipes for how to 3D print parts or how to use additive manufacturing to develop parts that the Navy needs for naval vessels. Michael specifically is with Industrial Inspection and Analysis, where they're kind of at the end of that pathway, inspecting those parts at the end to make sure that they're, as you all have said, to make sure they're going to hold up. That's the key thing. So with that kind of preface, and Phil, you talked a little bit about this, kind of that NDT is everywhere, but kind of talk about why is NDT such an important process in manufacturing, and specifically with what you all are doing, it's defense manufacturing. So why is this such a critical process?
So NDT in itself really hit the big back in the early railroad days, right? So that's basically when it became even somewhat familiar with anybody was the railroad days, where they used to use motor oil and talcum powder on the railroad lines to look for cracks. So as they were welding track together, they were realizing the track was cracking after a certain point, and they couldn't figure out why. So somebody came up with a completely absurd idea to throw motor oil down on it and then clean it off and then put talcum powder down. And as it bled out, you could actually see where the weld didn't fuse. That was the railroad industry. And then since then, it's grown mainly the Industrial Revolution, right? So the next big jump is the Industrial Revolution. And it was a lot of the construction side of the house started having a lot of failures in industry. So a lot of material started failing, a lot of other catastrophic events started happening. So then people started finding ways to actually inspect it to find out what was happening, why it was happening, and ways to stop it from failing. So the worst part about our job is the fact that our job came around because a lot of people died. Right, so there's a lot of our job is to stop that from happening, and so it had to happen for us to get. And so, majority of the time we're inspecting stuff, it's to stop that factor. Sure. So the Industrial Revolution, then from there, it was World War II was the next big jump. So after that, it's pretty much we've been nonstop inspecting everything since then. Weapon systems, submarines, the USS Thresher, right? That's where majority of the NAVC side of the house come from, or the sub-safe side of the house came from, was a Thresher, right? So Thresher had a huge fatigue crack, or cracking in the hull that caused massive flooding, and that was the last time, civilians were allowed on dive for initial. So now, all the submarines had to go through what they call sub-safe, right? So there's a much strenuous inspection process for sub-safe rather than just standard ship inspections. But yeah, so we inspect ships, we inspect subs, we inspect automobiles, roller coasters, the Carowinds, right? So there was the roller coaster Carowinds that had the huge crack in the actual support of the railing system. That's our job, is to inspect that to keep that from happening. So Disney World, Disneyland, they always have an NDT staff on hand just to inspect all the rides.
What are the main methods at this point you were talking about kind of that history and development of people figuring out how to do this. So what are those main kind of methods that are in play right now that you all see, out in the field or in your roles?
Yeah, so Phil was talking about the oil and whiting method of putting oil and then talcum powder on track. So that's liquid penetrant testing is what that's involved into. It used to be petroleum-based chemicals that we would use and put on parts and then just wash them down the drain. And, as ecological concerns and environmental protections have evolved, that's evolved just like everything else. So the big ones are the liquid penetrant testing, radiographic testing, which is an X-ray, just like of your arm. We do that of various materials and shapes. Ultrasonic testing, which is putting sound into a part, and we can either bounce it or send it straight back and up and down to see various places where we can't really reach sometimes. That kind of started in World War II, big time with the barrels on the big battleships, actually. Cool story there. But then we have visual testing, which is just using your eyes, looking at a part, comparing it to a standard, making sure it fits where it's supposed to fit, everything's sound and nothing's visibly showing. And then we have eddy current, which is one of the more advanced methods currently. I'd say phased array ultrasonics is probably the most intricate method we have currently. But then eddy current uses magnetic coils to put energy into a part and it detects super, super fine cracks. So like aviation parts, they use eddy current a lot to look for cracks in the skin, which is actually a structural component of the aircraft. And it'll actually work on non-ferromagnetic parts, so it's a very versatile method. So the other method would be magnetic particle, which uses magnetism. We can induce it in a whole bunch of different ways, in different orientations, and that's either use a dry powder and it attracts to a crack in the part, or we can use a wet liquid that will attract to the crack in the part, but it's a little easier to see because it's usually ultraviolet where it fluoresces.
So kind of talk a little bit about your, career journey, kind of some of the places you've put these skills to use. And then, with that, practically, when in the manufacturing process are these different kinds of processes carried out? So
my path started about 2006. I went to Tulsa, Oklahoma to go to a school called Spartan College of Aeronautics. I was really interested in aviation forever and thought it sounded neat. And my brother was going to be a mechanic, so I decided I wanted to check on his work, make sure it was safe, right? So I went through that program. While I was in the school, I started working for an NDT company. Started doing X-ray of honeycomb panels for aircraft. And then it turned into X-ray of anything aircraft and some eddy current and it was a fantastic experience to learn just a multitude of different methods and gain a bunch of hours of experience. From there, I moved back to Missouri and started doing x-rays of stainless steel pressure vessel welds. And I did that for a long time. It was really interesting. There's a lot of beer tanks, wine tanks, milk tanks, vaccination tanks. COVID-19, we shot all those tanks that they made the vaccinations in. Just a multitude of different tanks. And after that, I got this job. Came here to specifically manage the NDT program and work with guys on helping build the parts that keep our country safe. Yeah, so NDT can happen at any stage of manufacturing, anywhere from the steel mill where they're making the materials. We can check the molds there. We can check the material before they melt it to make sure it's the right chemical composition. We can all the way to the end where different components are welded together or fitted together. We can check at any stage anything that needs to be checked. We're very versatile, and like Phil said, we've had to become that way to stop the loss.
So for me, I joined the Navy in '98. After joining the Navy, I worked aviation for a couple of years. Found out about NDT through that process, and then ended up going to the school in 2007, or actually 2006. Finished in 2007, and have been doing it ever since. Right, so helicopters, airplanes. So I've worked on F-18s, F-14s, H-60s, 46s, 53s, some foreign aircraft that the U.S. owns, just different things about the world. But also when I was on the carriers, I would also do stuff on the carriers. So I was doing anything that touched an airplane on the carrier was my responsibility. So I was doing a lot of inspections on eddy current, mag particle, fluorescent, UT, RT, lots of experience in doing those shots. X-raying aircraft components, X-raying aircraft while they're fully assembled. Right, so like he was saying, in the processes we start from the beginning, right? So when they first start making the materials, all the way to the end of before it goes out the door. But then we also do it after that. So we actually inspect after in use, right? In service parts, so parts that are already out there working. So we know everything has a fatigue and fail point. And a lot of times it's already been calculated into its use. And so our job is to go back out to make sure it hasn't hit that fail point yet. Right? So even though we started at the beginning when it was first manufactured, nothing lasts forever. Right. And so our job is to go through the entire process from cradle to grave to where the product's no longer used anymore. All right, so I've shot X-rays. So after that, got on the Navy, I went and worked for a company where we did explosive ordnance handling. So we did X-ray evaluation analysis of ordnance and rocket motors and stuff like that. Some of the rocket motors I was X-raying were older than I was, and so we were just evaluating them just to make sure they were still in the service lifespan, and that nothing was deteriorated or broken with them, and they were still usable. And so that just goes to the thing that every 5 to 6 years we'd pull them out of cold store and then X-ray them and then send them back to cold store.
That's really cool. And what you're talking about, like, because I guess I've been in the NDT lab over for the ATDM program, and you see students with the generally smaller parts is what you guys are working with. So that's what I'm thinking about, that the pieces before they're going into use. But yeah, the idea of trying to X-ray parts on a helicopter that is assembled and figure out what's what, and that sounds fun and complicated.
Correct. Yeah. So it's not. So what we have in the classroom is just a classroom type environment, right? We can't really necessarily bring a ship inside the classroom.
Why not? Generally speaking, NDT, and you had talked about this, kind of goes very hand in hand with welding, and also obviously with IAA. IIA. You all are doing work very closely connected with additive manufacturing. So I guess talk about the difference between, I guess, even what processes you would use for those, if you're looking at a weld part versus something that was 3D printed, kind of just how does that look different between those two things?
Everything we do is different, but it's also
Stay with us. We'll be right back. When you need reliable results, IALR delivers. Our Applied Research Division works with businesses and universities on everything from product testing to process improvement. Our expertise spans chemistry, biology, plant growth, advanced materials, and more. We've got the experts, the labs, and the tools to get you results you can use. See how at ialr.org/research.
I mean, we gave you the big methods examples, but there's a bunch of techniques under each of those methods, so we can, ultrasonics, for instance, we mentioned phased array. There's ultrasonic conventional longitudinal, ultrasonic conventional shear wave, phased array shear wave, phased array longitudinal, total focus method, beam steering, there's tons of different ways. So essentially all the methods are the same. It's just how we focus in that energy and how we use different energy for different parts. So additive in particular, we're not looking for gross defects most of the time. It's usually going to be very small, very fine holes that the lasers missed when they were fusing different layers, or some spatter sometimes will stick in places it shouldn't stick. So we're looking for little BBs that shouldn't be there. Sometimes the powders don't get completely removed from the process, so we're looking for powder in holes that it shouldn't be in. And so it's all the same, but we can tailor it down and narrow it down to a very specific application, and every application is different,
So with welds, we concentrate strictly on just the weld and the area around it, right? So we call it heat effect zone. So we can actually control how much we look at, how much we inspect, because the material up to that point should have been inspected up to the point where the welder got it hot. And so with the weld, we normally care about the weld itself, the weldment, how it was fused, how the joint worked, right? So did they get the joint together like it's supposed to be? Did it meet the requirement of the code? And then the area around it where they heated it up during the welding process, right? Because those are the areas that are going to change the characteristics of the base metal. To where, like with additive manufacturing or something like that, you would go towards the casting side, to where they're basically in a casting, you're pouring hot molten metal into a mold, and then you're letting it cool. Well, and with their additive manufacturing, you're taking away the mold factor of it, and now you're just fusing certain points in the metal together. You're not just hot pouring metal into a big green mold, right? And so you're looking for different discontinuities based on the differences in how the processes work. And that's what our job is to do, is to take how it was manufactured in the first place. All right, so what was the initial point of manufacturing? So was it made in a foundry, right? So to come out of foundry as a raw stock material, right? So you have a big plug of ingot, right? And they'll cut out sections of it, and they'll send it off to get forged. Forging discontinuities are nothing like casting discontinuities. So when you go to cast something, you get the metal molten hot, and you pour it into a mold. Those are loosely bound grain structures, right? So you've got big grains of like mass. They're not really fine compressed, to where if you send it off a piece of metal off to a foundry to where it gets forged, like a sheet of metal, they actually take that hot metal, not molten, just like to the point where it's malleable, and they'll continuously roll it flat until it gets to a specific height, and that's how you get your metal. That's how you get the sheets of metal out of it. Because they roll it from a big chunk to get smaller, add more and more pressure, and it stretches the metal out until it gets to a very specific thickness. But by doing so, it takes all those grains and makes them small. So it makes it more compressed, more compact. So it makes it easier to inspect because they're actually more uniform grain structures. And to where like a casting or a 3D printing, the grain structures aren't uniform in nature. So it requires a different understanding and different processes, a theory of concept to evaluate and inspect them.
Currently at the AMCOE, we use laser powder bed fusion. So how that works is there's a build plate and a machine pushes a layer of powder over that build plate. And then there's a high-powered laser that fuses that powder into the build plate just instantly. And then after that layer is done, it makes another layer of the powder, puts the powder down, fuses it with the laser, and then just keeps going up and up and up. Most layers are sub half millimeter thick, so they're not thick at all. So it's very thin, that's very fast, and it makes a part that is just almost ready to go in service, depending on the application. So there's very little machining required to clean up a laser powder bed part. The other modality we do over there is directed energy deposition, or WAM, wire arc additive manufacturing. So it's just like in a shipyard, you see a guy with a MIG welder and he's just welding. We just put it on a robot arm and it just welds a layer and then goes up a layer and welds a layer and goes up. So each of those modalities we're testing for very different things, and each one is challenging in its own right. So DED is more like a traditional weld, but it's stacked weld, so it adds a level of complexity that's very different. It requires a lot more machining after it's finished to get a usable part out of it. PBF is close to ready to go, but the surface is still rough, so most of the NDT methods are not applicable until it is machined or cleaned or smoothed, or they're developing different ways to prepare that surface for NDT before they go in service. So there's a little blurb for you on what we're printing.
Yeah. It's not simple. It's not one size fits all. The process has to match how it was manufactured. As the obviously, a lot of those details I don't fully understand, but that's the part I can get in my brain right now.
Our job in the industry is to determine exactly what we need to inspect, right? How we need to inspect it, based on where it came from. And because we can sit there and inspect stuff all day long, but if we don't know where it came from or how it was originally manufactured, then we're wasting our time. And we might not be looking for the right discontinuities, right? We're not looking for the correct indications. If it was a welded part and I'm just trying to, do a quick visual of it and don't really care about anything else other than a visual. I've seen some pretty welds, some beautiful welds. You go look underneath it, horrible. Absolutely just the worst thing you've ever seen. But you can't look underneath it with your eyes. You have to use some other method.
And obviously you all have different roles, Phil, with more obviously training students who are actively looking to enter this field and get an NDT job. Michael, I know you're more kind of leading a team of people who are already in this field. But what does this, I guess, career field look like? What are kind of the pathways that people can go? And I know there's like the different levels to this too. So if you guys want to talk about that as well.
I'll go and start off, seeing how my job is pretty much about putting people in the industry in the first place. Mm-hmm. So as far as like placing students goes, we can place students just about anywhere. We try to concentrate on the DIB, SIB, and the MIB, right? So the Maritime Industrial Base or the Defense Industrial Base, or the Submarine Industrial Base while we're at it. We try to get them in those industries, right? Those are the industries that this program is set up to establish, to put them into. But the level of training we give them, the actual knowledge itself, is applicable to any industry, right? So NDT in of itself isn't only solely dedicated to one industry, right? So it's one of those things where I've had students leave here and get a job at, a shipyards all day long, but at the same time, I've had students leave here and actually pick up a job where they're inspecting power plants, critical infrastructure, right? So they're going into the nuclear power plants and doing NDT inside of a nuclear facility, inspecting to make sure while they're doing plant shutdowns and rework, so that way they can get to understand, but it's completely different theory altogether. Then I've got other students who are manufacturing components for the Navy or the Army or even anybody else, the Air Force, right? They're making tanks, they're making armored vehicles, they're making airplanes, they're making whatever. So they're going into those fields with just the knowledge we give them. And
which again is in 4 months. These people are coming in with no previous knowledge of this. Yeah.
I've had baristas. Last cohort had a school bus driver, right? Drove a school bus for several years. She was, I don't want to give her age away, but she was a little older. Let's say between the 30s and 40s, and just complete career change, right? I've had a student in his 60s come through, complete career change, right? So come through, got the training, then went out and was successful. So there's not set to a specific age group. Anybody can come to this program. I've had 18-year-olds straight out of high school, left high school in June or May, June timeframe. August, I showed up here to go training and left here and made $45, $50 an hour. And so just the program itself is a very great benefit to the industry, right? So our program provides, we have employers all the time who like our students because the way we train, our training program works, how we train them, what we train them to, how we need them to understand NDT. And so while that was a very rare case that we got that for a student at that point, but there was a job out there that paid it. So yes, there's always opportunity out there for any industry especially for NDT. There's always a need.
Yeah, I love, as you know, those stories that you were talking about of people coming with no previous experience in career fields that they're not fulfilled in, and then in 4 months they get to do something that they are fulfilled in and make good money doing it. So
in NDT, you're not stuck in any industry. You can switch industries. So yeah, one day we can go to a power plant and X-ray a bunch of welds on piping in a system, and then the next day go to an airport and do X-ray examination of aircraft parts. The next day we could go to SpaceX and X-ray a space part. It's very different. And when I say you can truly find something in whatever you like, I really believe you can. So once they leave the ATDM, when they come to me, they're a trainee still. They have the experience, they have the some hours, but typically not enough hours yet to get the level 1 certification. So the level 1 certification is a person who has some experience and training in the method, but they're still learning. They still have a ways to go, so they have to operate under the supervision of a level 2. The level 2 is responsible for completely taking a method outside, away, independently, and doing that method efficiently and correctly. So they can take a level 1 and give them the experience hours to get them up to a level 2, where they go on their own and start training people under them. So it's kind of a self-feeding career field, if you will, too. So level 2s, there's a lot of people who like to be level 2s and they just stay at level 2 forever, and there's nothing wrong with that. You can make good money as a level 2. You could go do shutdowns and turnarounds in power plants and collect your per diems and your high wages and what's the prevailing wage. There's a lot of prevailing wage federal jobs out there that travel around and pay really good money. So there's nothing wrong with being a level 2 forever if that's what you want. Guys like Phil and I, we wanted a little more, I think. So we just kept going. We liked learning. We liked teaching. We liked figuring out the problems that sometimes a level 2 can't figure out. So we have our own set of skills as a level 3 to share with everybody, and to write the procedures that the level 2s have to follow when they're doing the testing independently to make sure everybody's safe.
So yeah, again, I think it's cool to see, the different ways that you all are involved. And obviously this is a very important career field, as you said, in any industry, regardless of what it is. If people are touching it, if people are riding on it, whatever the thing is, NDT is involved. So it's a very important industry. And just seeing the roles that, these two projects are taking with that for obviously ATDM training the next wave of people who will join this industry and be able, particularly in the defense and maritime industrial base, be able to, inspect these parts, inspect these welds, and make sure that all these ships and submarines, whether it be inspecting the original part or inspecting something on a submarine way after the fact, or whatever that looks like, be able to do these types of inspections. And then obviously, Michael, with what you all are doing with making sure that these recipes, these technical data packages that the Navy is creating for their suppliers, that those right processes are built in, and for how to inspect these parts. It's really, really cool. Is there anything else that you all would want to add about just kind of NDT in general, or the role that you get to play in this field?
I enjoy my role. right? So there's not too many people who actually enjoy teaching NDT. They find it pretty difficult. This is one of the things I actually enjoy doing, because it's very fulfilling to watch a student grow, right? Get them to understand what NDT is in the first place, and then watching the light bulbs just start clicking off in their heads. And then once they start realizing, because you can sit there and talk to them all day long about what NDT is and what it does and how important it is in the industry and how important it is in the world. And they don't understand until they actually start looking and they start doing their own research. And they're like, holy cow, it's everywhere. And they start applying to jobs. And they start realizing, yes, they can get a job at SpaceX. Blue Origin is hiring. You can go Tesla, you can go Lockheed Martin, Newport News shipyards. We have everybody in every industry and we were in everything, but we're just the unknown, right? So once something fails, then it's always the NDT person. But up to that point, nobody really knows what we do. We're kind of like the ghost that sits in the background to make sure that nothing fails. And so until something goes catastrophic, nobody knows who we are or what we do. And so it kind of creates a mystery behind it, but honestly, I openly talk about what we do all day long because I enjoy teaching, right? So I enjoy sharing my knowledge and sharing my information and watching people grow in the industry.
Over on my side of things, in the production side, I have an ATDM graduate, and we've been working with him, getting him his hours, and he's doing great. He came over with, enough knowledge that he's able to just jump right in and start helping out. So that's I can personally attest to the fact that ATDM is putting out great students. One thing I would add is just get comfortable with computers. Learn computers. If computers are of interest, you can go into NDT just doing computers at this point. AI is becoming mainstream in NDT, machine learning, programming robotics, operating the ROVs and the underwater robots, the remotely operated vehicles, quadcopters, yeah. I mean, I know a guy he's a level 3. His job is to collect the drone data that people collect across the country, and he just sits at his computer and reviews it, looking for defects and says, hey, go look at this closer. So just learn your computers. Your reporting is going to be computed. It's not going to change. There's no way around it. You can avoid it for a while, but I think in a few years it's going to be completely unavoidable. And change is good. That's the growth in our industry, all the way from back in the steam boiler days and cracked tracks, and all the way through now with leading edge computing and AI and machine learning. It's coming, and I think it's a good thing as long as we continue to monitor it.
I think we should all try to do the underwater robots you were talking about. That sounds pretty cool. That'll be my next job. So thank you guys. I appreciate it.
3, 2, 1, let's go.
At IALR, we're training people for careers supporting the construction and maintenance of ships and submarines. ATDM, or Accelerated Training in Defense Manufacturing, gets students ready for defense manufacturing careers in just 16 weeks. Skills like machining, welding, additive manufacturing, non-destructive testing, and metrology. The best part? Most graduates land great jobs right away. If you want a fast track to a career with impact, check out atdm.org.